Okay, folks, welcome to this third session. My name is Omar Chowdhury. So this is joint work with my colleagues at Syracuse University and my PhD student, Hammad Mazhar. As Ioana was mentioning, couldn't be unfortunately here because of visa issues, and hence me presenting. So the title of the paper is MAVERICK. What we are trying to do is an app-independent and platform-agnostic system to enforce policies at runtime. Now, I'll give you essentially bits and pieces of it, what each of these mean in a bit. Okay. So before that, I wanted to give you a slight skeleton of the talk. I wanted to talk a little bit about background and the motivation. Tell you a little bit about prior work and limitations. And then the third thing I want to do is like formally set up what the problem is we are trying to solve and complexity. Thanks to Alan Turing, I'll tell you the problem we are trying to solve is undecidable. And then I'm going to talk briefly about high-level aspects of the design of MAVERICK and the evaluation. And if I have time, I'll talk about summary and future work. Okay? Now, let's talk a little bit about background and motivation. So let's start off with programmable IoT systems. So these are IoT systems where you have IoT devices which can be connected by IoT backend that are first party or third party. Example would be Samsung SmartThings. And what the feature of these are, you can install apps. These are automation apps that tells you when you walk through the door, oh, switch on the light. Okay? Simple as that. And you can do other complicated stuff. Now, the IoT devices also interact with the environment. So environment here could be, say, temperature, moisture, like switching on the light physically. And then there are these third-party services like IFTTT. So physical actions can influence the state changes. And that gets propagated to the cloud, which the app then takes over. Based on what automation you set up, it will do something. Okay? And based on whatever you have observed from the update, then these apps can do some actions, like switch on the light, right? When I walk through the door, the motion sensor senses me, sends the update to the IoT backend. I have a rule that if the motion sensor gets triggered, switch on the light, okay? Now, so this is the overarching idea, but the issue is that bad things could happen if you allow all these complicated interaction, and our hope is to block this bad things. So let me give you an example of what are such bad things. Now, assume you have a home with smart IoT system, and you, being a nerd, you programmed it and installed a bunch of automation rules, okay? Now, what you wanted is that once you leave the home, your door should be locked, okay? That's something you wanted to do. And what could happen is that the cloud had a weakness where an attacker could come and kind of exploit this weakness and open the door, okay? Now, this is not something we want. Or you could have a situation that when there is a leak, you have the rule that says turn off the water valve. But once you turn off the water valve, you have a fire. There is no water in the sprinkler, okay? This is a hypothetical situation that in that case, fire would spread, and all these safety measures are useless, right? So the obvious question is we want to avoid these systems working unexpectedly. Now, what is unexpected is the user's job. We don't know what is unexpected, right? Now, so what do I mean is that we kind of label this problem the IoT system safety problem. And the name is kind of inspired from the access control world where they have this safety problem. Now, what is safe is up to the user, right? It could mean security violations, being unsafe. It could be physical safety. It could be privacy violation. So it's an umbrella term to kind of cover all of these, okay? And what we want is that you want a IoT system to transition to an unsafe state or correct it afterwards, like based on some policy. Now, you might say, if you can prevent the IoT system from transitioning to a bad state, why do you need to bring it back? Because the thing is, the state transition can happen due to a human action, human switching on the light. And it can start a cascade of issues. Okay? Now, what this would look like in real life is that when this goes away, the same attack would be launched, and an unlock would be attempted, but my policy says that a smart lock remains locked while away, right? So whenever the backend gives you this command, it violates the policy, you're not going to open the door. As simple as that. Now, so the other situation, let's talk about the second case of the water leak. The leak was detected, and you switch off the water valve, okay? But whenever there is a fire, you wrote that smoke is detected, and you wrote a policy that valve remains open while smoke detected, okay? So in that case, what you do is you take a corrective action and switch on the valve. Now, if you have worked on access control, this is essentially what is known as user obligation, system obligation, that the system takes corrective action to fix the system's bad state, okay? So that is the high-level idea. The next, I want to talk a little bit about, okay? So talk a little bit about prior work and limitations, including, so this prior work includes my work too. So a bunch of previous work mainly worked on the app side of things. So rather than looking at the whole problem, we looked at only the app's interaction. So the idea was that apps come from untrusted sources, so all bad things that happen to the system happens because of apps. So many of our work essentially instrumented these apps to enforce policies, okay? But turns out that is only a partial picture, because there are other interactions that could take the system to an untrusted situation. And the policy checker, after instrumenting the app, so whenever the app tries to do something bad, it would essentially block. So all the defense dependent on the apps itself. Now, they never talked about environment, and neither they talked about third-party services, because the main issue was you needed a common choke point that would allow you to visit, see all the actions coming to the devices. Otherwise, you won't be able to enforce things, okay? Now, the other issue is that because just looking at the app, it induces a weaker threat model, okay? And makes it app dependent. And finally, it's platform specific. All the implementation of the papers I talked, including ours, we all implemented it either for Samsung SmartThings or implemented it for OpenHAB, right? It was not platform agnostic. So what we wanted to do in this paper was to develop a platform agnostic and app independent solution to the safety problem, because app independence is important because not all services allow you to modify apps, right? Like IFTTT. Like if you are connected to an existing IFTTT applet written by somebody else, you just cannot go change it, okay? So we wanted something that is both platform agnostic and app independent. Now, as I mentioned, I wanted to give you a problem definition and complexity in respect of Alan Turing. We'll see why in a bit. So IoT devices, if you think about it abstractly, can be viewed as essentially a milli machine, okay? Where you have actions which are denoted by green, and that can be issued to it, like say lock and unlocked, and it then communicates back to the system a system update. Say, for instance, if you're in the lock state, you issue the unlock command, which is the left edge? Yeah, the left edge. In that case, you would give the unlock status that tell the system that the door has been unlocked, right? Now, if you think about the whole system, your state is essentially a Cartesian product of all of the state of the devices, okay? Plus the environmental state. Now, so if we look about programmable IoT system, this Cartesian product can be looked at as a label transition system, where you have states corresponding to the different devices, and you can take actions to kind of navigate between these states, okay? And some of these would be valid states, some of these are unsafe states, okay? Now, if we look at it, the formal problem definition, before we do that, I have to tell you what is an IoT system, which seems strange. Formally, this would be, you have an IoT system is a tuple, which consists of states, variables that tell you the device states, domains these variables can take values from, like temperature takes values from real numbers. Then you have actions, like unlock the door, lock the door, and real transition systems, transition relations that I mentioned. And what we want is that for the problem definition, the other aspect we need is a policy. This is psi, which takes a state and gives you a pair. The first of the pair is a Boolean, true or false, whether this state is safe or unsafe, true being safe, false being unsafe. And the second component, phi, tells you if it's unsafe, what are the sequence of actions that get me to a safe state? This is the corrective action, okay? And these are, so the A sub C is essentially the cyber actions. You cannot do physical actions, right, with an actuator. So the policy, if you look at it, it can essentially partition states into safe state and unsafe state. I showed the kind of green and red annotation in the label transition, the green being safe and the red being unsafe. Now, so the IoT system safety problem requires that I either never moves to the unsafe state, or if it moves, I should somehow have a way of bringing it back to a safe state, okay, through a bunch of iteration. Now, the thing is, we proved the decision version of it. The decision version is actually needed for policy analysis, I'll tell you in a bit, is actually undecidable, and you can encode halting problem to this decision problem. Now, this is not very surprising because the problem skeleton has been seen in other kind of problem domains. Say, for instance, the IoT, the access control safety problem. But turns out you can make it tractable by making some assumptions that in many cases hold in real life. So intuitively, you have finite number of devices, states, and actions. Now, you might say, like, states, you said temperature could be real. Between any two real numbers, there is infinite number of real numbers. So how can it be state? But the thing is, like, because of precision, if we think about two-digit precision, it is finite, right? And so you can make such, and if you have concurrent actions, you can assume somehow they get serialized. And policies, rather than trying to, I'll say, bring the system instantaneously, you allow it to over some time, that eventually it becomes stable. And so you can do other things that devices always act faithfully. Communication is reliable. Finite devices in your system. You have finite variables. You have, at each step, there is one single action that is happening. And at most, one invariant gets violated. Now, if you were to make all these assumptions, you can reduce this problem, the decision version, to a model checking problem that is solvable. Okay? Now, what this entails is that we get a stronger threat model because of the general look at the safety problem, where the users write a policy, and if there is a physical action, there is an update, and as a result, you will get a cyber action, or the third party does a cyber action, then you try to block it. Okay? Now I'm going to talk a little bit about design and evaluation. I might skip some of the slides if I'm running out of time. So the first thing we need to worry about for Maverick is that I told you there are all this information flowing. I need a choke point. to put this so that it gets a visibility of the whole thing that is happening. And so it sits as an intermediary between the backend and the IoT devices, and it assists in policy definition and enforcement. So if you think about the user and the device on the left and the IoT backend and the third-party web service on the right, so what it does is Maverick sits in the middle. So there is automation interface that it talks to the different automation services. Then it has the device interface with which it talks with the different devices. And there is an aspect of policy authoring, which is the invariant synthesis and policy analysis. I'll talk about it briefly in a bit. And then you have the policy checker, which essentially the user can interact with the invariant synthesis and policy analysis engine to write policies. And then you can install it in the policy checker, and the policy checker will check and do any corrective action. Okay? So let's talk about, to be honest, when we designed the system, usability was never a concern. We wanted to build a foundation first. And one of the criticism we got is like, your policy language is so complicated that people cannot write policy. So we took this criticism. It's a constructive criticism that we are still working on. So what our policies look like are pairs. The first part is actual invariant. That is, when I'm away, the door should never open. Okay? The second part, CJ, tells you what happens, what should you do if that invariant gets violated. Somebody opened the door when you're not home. What do? You close the door, right? That's essentially what is corrective action. And the corrective action could be a sequence. And so the idea is that a system state is considered unsafe, it violates one of the invariant. Okay? And if it's violated, then you do the corresponding corrective actions. Okay? Say if the intended policy smart lock remains locked while away, the Maverick policy would look like something like this, that when the home mode is away, then your smart lock should be locked. Otherwise, block the unlock command and send the lock command. Okay? Now, this is what the policy language looks like underneath. We did not even try to hide it that by kind of creating a surface language. We intentionally made it like a propositional linear temporal logic. And so how do we help users write policies? So the basic intuition is there are two sides to it. Policy analysis and invariant synthesis. Now, invariant synthesis, the basic idea is the user tells you a sequence of events. It's going to tell you, this is the sequences where bad thing happened. You don't even have to tell me what bad things are. You just tell me that this trace contains bad things, this trace contains good things. Okay, now what you get back is a candidate invariant that you choose from. You add corrective actions, and then you create a candidate policy, which you feed it to the policy analysis. The policy analysis is what solves the decision problem of ISSP and gives you feedback. When this is good, you get the final policy. Okay. Now, because I'm running out of time, I'm not going to talk about details. So we did evaluation both on virtual and physical test beds. I just wanted to touch on RQ 2 and 3. The first one is regarding whether it's effective. The third one is being what is overhead. So I'm gonna just talk about, so what we did was that we generated both malfunctioning and benign events. And what we realized is that it's effective. It created like the correct action rate 100 times. And so it is effective, at least for the sequences we generated. And so if you think about overhead, the latency is very low, but our throughput kind of diminished substantially when we installed Maverick. It's likely because of two reasons. One reason could be there is a bug that we are still yet to find. The other one is Maverick actually runs as a cron job. And as a result of this, it sort of killed the performance. So our overhead throughput decrease is pretty bad, like at times like 35x. And so, yeah, but latency-wise, it's not too bad. Okay, so I think I want to talk a little bit about the summary and future work. So what I presented is MAVERICK. It's a platform-agnostic app-independent intermediary for IoT system policy enforcement. And we allowed semi-automated policy generation and verification, and tractable policy enforcement and analysis under good assumptions. So what we are doing currently is we are trying to use techniques from automated program synthesis, especially SIGAS, to do fully automated policy synthesis. And we are truly trying to improve the usability of MAVERICK in two respects. One is how to help users to write policies. Maybe take help from ChatGPT kind of interfaces where they write in natural languages. I know it's a pipe dream, but might work. It seems like a hype. The other one is, which we kind of dusted under the rug, is how do you set this up, right? You need to put this middle box in the middle and connect with everybody, right? And so this is only can be done easily for nerds like us, but normal users cannot do that. So how can we help them set up the actual architecture that way? And the other one is improving the scalability. We might have a bug, or it's because of the cron job. So we ran profiling but couldn't kind of figure out exactly what's happening. And that's something we're working on. So any questions, I'll be more than happy to take. So if you have more detailed question about implementation, you should email Hammad, because those I don't know about. I just only know about high-level stuff. But if you have questions, I'll be more than happy to answer.
OK, let's thank the speaker.
Yeah, thank you.
Hi, I have a question about, you were talking about incorporating all these heterogeneous different devices, and I was wondering how exactly that was going to work, because I know the way that all these different IoT devices work is they usually have their own companion apps, and those companion apps, they want you to use the companion apps versus using something that works for everything, because they want to incorporate maybe a cryptography or some kind of protection that protects that communication to that device. So how are you going to scale that, or would the scaling work for that? That's going to incorporate all these different devices that have different cryptography and all that kind of stuff.
Yeah, that's an excellent question and a valid one at that. So most IoT devices do come with companion apps, but they do allow integration with third party, right? So you can use that binding. Like say, for instance, they allow MQTT binding. You can use that, right? You can put the middle box and communicate that with MQTT. Then you're done, right? Okay. So we essentially use that. Now, that being said, can I guarantee that MAVERICK supports everything under God's art? No, I cannot. Like if there are certain things that do not allow third-party integration, there's nothing we can do. Right? We essentially exploit that integration.
Okay, thank you.
Other questions?
We're running out of time, so I think for interest of time, we'll ask Omar more questions, including myself. I have some questions for the break, so let's thank Omar again.
Thank you, folks.